Reservations in two-way slabs by means of yield lines. In this video, we will handle a case 17, which is part of the 1620 cases. And this is about a slab where three sides are fixed and one side is freely supported. This is case 17. It's a corner left hole. We have a rectangular slab with sides A and B, and it's a two-way slab, so B must be between A and 2A. And we make a reservation in the corner, and this reservation follows the yield line. So D1 over D2 gives you the angle of 60 degrees. It's this one. Then the top left corner, it means that D4 and D3 is 0, and D3 is here and D4 is there, must be 0. And you only cut one yield line at the bottom, so D1 is between 0 and S4. We look at the yield lines. This is for the negative bending moments on the supports. The yield line stops where the reservation is. Then from where the rotation axis intersect, at the starting point of a new yield line going to the left-hand side. On the bottom, the same. We use the 30, 60, 45 rule. So this is 60 degrees and this is 30 degrees. So you end up here. This is 45 degrees on both sides. And we have the yield pattern. We repeat the conditions and we write it properly. And to visualize it, the black lines is fixed and the light line, the left line, is simply supported. See, it's just a very simple reservation following the yield line and getting bigger until here. Let's calculate the work done by the external forces. This is when looking at the orange part, rectangular. So we have this distance is B minus S1 minus S3 multiplied by A, and the mean deflection is delta over 2. Then we come to the green parts. We take the total area, which is A times S1 plus A times S3, but we have counted now. We have to subtract the reservation. And then we have two triangles. You have the one D2 times D1 divided by 2 in this direction. So it means divided by D1 over S4 or multiplied by D1 over S4. And then from this triangle, you project, it's a rotation, not a projection, a rotation around this axis. So it means that the maximum deflection there is D2 over S1. This is S1 and this is D2. And then we have this formulation. We fill in the different parameters and we got the expression. The work done by the internal forces. Then we look at the yield lines. We have first this negative bending moment. It's M minus, of course, D2 divided by the angle of rotation, which is delta over S4. Then we got this line. It's the same projected to this of rotation. So it's B minus D2 divided by S4. On the bottom, we have this line projected on this axis, and we have this line. So we have 2 times B over S2. And of course, here we have 2 times A over S3. And here we have only this portion of the yield line, which is projected on this axis. And this is A minus B1. And the maximum deflection is delta over S1. Fill in the different parameters. We say A is equal to D. We get M from it. And that's the formula for the maximum bending moment. It's a function of B over A and alpha 1, which is D1 over A. Remember, D1 and D2 are fixed because of the following the yield line. Let's give an example for a square slab. with 160 millimeter depth, 30 millimeter concrete cover, loaded with floor finish 2 kilonewton per square meter and a mobile load of 12. And we want to make a reservation of this size in the slab. What is the needed reinforcement in this slab? We calculate the load in ULS, ultimate limit state. It's 1.35 times the permanent load plus 1.5 times the mobile load gives me 26.1 kilonewton per square meter. These are the different parameters. I work with parameters without a dimension, so that's why I divide everything by A. Maximum bending moment is then equal to 17.1 kilonewton meter per meter. The lever arm, we can calculate the mean lever arm, which is 122. And from that, we calculate the needed reinforcement, which is 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the keel reinforcement. And we have 394 square millimeter per meter. This means 8 diameters, 8 per meter, and gives you 402 square millimeters per meter. So you see that you can very quickly reinforce a slab with a reservation like that. The second example is an existing slab, and the people ask you, can we make a small reservation in the slab, only 1 meter by 0.6 by a slab of 5 by 5? But we do not know what the reinforcement is. We don't know what the initial load was that was calculated for. The only thing we know is that the reinforcement top and bottom and in all directions are equal. So what can we do? We can calculate the maximum bending moment without the hole, and the maximum bending moment without the hole. Therefore, we take M0 and divide it by the load because we don't know the load. Then on the right-hand side, you only have a formula depending on geometrics. We can calculate this and we find that it's 0.5 or 0.6. Then we calculate the maximum bending moment with this hole. So with this alpha 1, and alpha 1 is then 1 divided by 5. Then we get 0.646 meter per meter. So this means that the bearing capacity is 92%. So that means by making this small reservation in the slab, you lose already 8% of the bearing capacity of the total slab. Now, the bearing capacity is defined as 100 times maximum bending moment without the hole divided by the maximum bending moment with the hole. Written in a formula, it's like this. We use parameters without a dimension. And we know that for case 7, we have to, case 17, for case 17, we must fulfill those two conditions. This is then the formula of the bearing capacity, but just filling in D1 and D in the previous formulas. We can put this in a graph to study this. And alpha 1, we vary between 0 and 0.5, because otherwise it's not a case 17 problem anymore. And on the y-axis, the bearing capacity, and we do that for different values of alpha. So the total range is between 1 and 2. And this is the total range between the black curve and the red one. For instance, to visualize it, this is the slab alpha is 1, so it's a square, and alpha 1, this element is 0.364 times the size of the square, the size of the square. And that means that we are on the red curve. And when you have 0.364, which is here, around here, and this is the maximum loss that you can have in bearing capacity. Then we can go to the other curve, the blue dotted curve, if alpha equals 1.5 and alpha 1 0.416, which is again a maximum for the alpha equals to 1.5, and you have this 92%. And then at last but not least, we have with alpha equals 2, and then we have also the maximum, which is this value. So you see that the maximum occurs with a different alpha 1, and this maximum depends on alpha. You can see that this is varying. A reservation of type 17, which is following the yield lines of a rectangular concrete slab, leads to a loss of bearing capacity of maximum 9%. And to visualize it, you see those two limits of a type of a whole